Hello, and welcome to this series of lectures about variations on the Turing machine model, the Church-Turing thesis, and undecidability of the halting problem. I've been asked to introduce myself. I'm Eric Allender. I'm at Rutgers University, and I've also been asked to say a little bit something about my background and how I happened to end up in the field of complexity theory. I grew up in a small town in Iowa, Mount Pleasant, Iowa, and when I went off to college, I was very sure I wanted to be a theater major and started off studying theater, but I also, just as a backup plan, decided to double major in computer science because I'd been exposed to some computers as a high school student, which was not so common in Iowa in the 1970s, but I had a great math teacher who had brought a computer in and let us play with it. And so I had enjoyed that, and I always liked math, so I figured, why not be something to fall back on. But then I discovered the theoretical courses in computer science. They really fired my imagination. It convinced me that there was really cool stuff going on, and I got some encouragement from professors and applied to grad school, went off to Georgia Tech, and it's been a love affair with complexity theory ever since. I've been at Rutgers basically my entire professional career. I'm a former chair and getting close to retirement now. What do I work on? I work in computational complexity theory, the study of different complexity classes, especially subclasses of P, but also larger classes, and circuit complexity, Kolmogorov complexity, and lately focus of my attention has been the minimum circuit size problem. It's a problem actually fairly closely related to Kolmogorov complexity. Both of them ask, given a string, how hard is it? How much information is in there? Or how hard is the truth table represented by that string to compute as a function? This is something that is going to be intractable if cryptography is ever going to be a reality. But there are various obstacles that seem to stand in the way of our proving that it's NP complete. And it's interesting for a lot of other reasons. And I'd be glad to talk to people about it at greater length at another time. But it's time now to start reminding you what you should have learned from previous lectures, and also to have a preview about what lies ahead. So with luck, this is a picture that should look sort of familiar. This blob here represents the Turing acceptable languages. These go by different names. Sometimes they're called the recursively enumerable sets. Sometimes, since recursively enumerable has got a lot of letters, we just call it the RE sets. And back when I was a grad student, that's what they were called. But then shortly thereafter, people decided, you know, the word recursive is kind of a bit of a pain here. So why don't we call them computably enumerable? Highlight the fact that it has something to do with computation, and that would be abbreviated the CE sets. But a lot of people didn't get the memo about that, and so they still call them the recursively enumerable sets. And I'm likely to use any of these terms and not be entirely consistent, so be prepared for that. And one thing that I hope you learned from the last lecture was that the decidable sets occupy this very interesting region. Something is decidable if and only if it is both recursively enumerable and co-RE. And the decidable sets are sometimes called the recursive sets. So the co-RE sets are those sets that are the complements of the RE sets. And that is the region we're talking about. Part of my lectures will be to explain why these classes of sets really do capture an important part of any kind of notion of computation that you're likely to actually run across, no matter what that model of computation might be, as long as it looks something like programs. And also, we will be highlighting the existence of a few problems over here in this region that is things that are Turing acceptable or recursively enumerable and not decidable. And we will see some important examples of things that are not computable. So fasten your seatbelts. That's what lies ahead of you for the next few lectures. Until then, bye-bye.